Okay, hello. We are still doing circuit examples. And yesterday I was solving the, relatively three equations, three unknowns. You can call that complex algebra if you want. And I found an error, and the reason why I found an error is because um, is because I recognized that if you go around the loop, the big loop here, all the potentials should add up. Uh, um, Kirchhoff's loop rule, and in other words, delta V should equal delta R1 plus delta R3. Sorry, delta V, the battery's potential difference, should equal the potential difference across R1 plus the potential difference across R3 using Kirchhoff's loop rule, and it doesn't because the potential difference across R1 plus the potential difference across R3 is greater than 12 volts. And the error was a silly algebraic error, which we all make all the time, and it's the yellow circled equation with two arrows. That was, had a 1 there, and that should have looked a little weird. Actually, it should look really weird because this is an integer and this is something with units. So these do not have the same units, and this should have been R1. So this should have been R1 under that fraction. So this should have been, so going down to the next line, it should have been 10 plus 10 plus 10. It should have been 30, and so I2 should have been 12 volts over 30, which is 0.4 amps. That means I3 should be 0.4 amps. That means I1 should be 0.8 amps. And so that means that coming back to the results, here we should have 0.4 amps, 0.8 amps, and then this is all so much nicer. It's 8 volts and 4 volts, right? So delta V1, the potential difference across R1 is 8 volts, and the potential difference across each of R2 and R3 is 4 volts. Much better symmetry, and we're done. Okay, that was the correction for that problem. So I've got just two more examples I want to do in terms of circuit examples today. Yesterday I had said I had 5. I might have said 4 at one point. I said I had 5 and I had done 3. I had made an error on the third one, just fixed that algebraic error. So let's do the other two. So the next circuit example is this one. In this circuit example, I've got 5 resistors attached to a single power supply. I just, for the heck of it, gave each resistor R1 is 1 ohm, R2 is 2 ohms, R3 is 3 ohms, etc., and the power supply is 10 volts. And I want to know what is the equivalent resistance for this circuit and how much current does the battery supply. So this is just an equivalent resistance question. We're looking for things in series and in parallel. And so we start, again, with part A by just looking for what is in series and what is in parallel. Well, to start with, and remember, sometimes the question could be asked and the answer could be there is no way for us to find the equivalent resistance. There is actually another method that we haven't learned in this class for more complicated circuits. But if nothing's in series or parallel, then you can't find an equivalent. We don't have the tools to find equivalent resistance right now. Okay, so anyway, so the answer could be there is none, or we can't find it. But in this case, we can. So we're looking for R1, R2, R3, R4, R5, what's in parallel and what's in series. Again, if there's a junction between two, like for instance, there's a junction, let me go ahead and indicate the junctions. Sorry, I'm having issues. Okay, so there's a junction here and a junction here, right? And so R2 cannot be in series with R3 or R5. R1 cannot be in series with R3 or R4 because there's a junction. But there is no junction between R4 and R5, so R4 and R5 are in series with each other. So we can go ahead and say they're in series, so we can write the equivalent resistance for those two in series, and we can simplify this circuit just a little bit, right? So I'm going to go ahead, we're going to run out of room pretty quick. I'm going to go ahead and redraw this circuit and say, okay, R4 and R5 are in series, so there is an equivalent resistance right there. This is still 1, 2, and 3, but the equivalent resistance of R4 and R5 is R4 plus R5, which is 9 ohms. Okay, Now we look for, is there anything else in series? Currently, there is nothing else in series because now all four of the resistors in our new little red circuit, all four of our resistors have junctions before they get to something else. So none of those resistors are in series. And yes, the battery is in series with resistor R1 and R2, but when we're looking for equivalent resistance, we're looking for resistors in series. Okay, but now, so then let's look for things in parallel, and indeed, hopefully you've already seen that that R3 has two wires in parallel with R2, right? So those two wires are in parallel. So with our equivalent, with our equivalent. It is not in parallel with 1 or 2 because it doesn't have two wires in common with 1 or 2, but it is in parallel with our equivalent. So we can write another equivalent circuit. So now we can I just went back to a blank page. We can write the equivalent of what we had was, we had R3 and the equivalent resistance of R4 and R5 in series. I'll just write that as R4 plus R5. And so now where that is the equivalent resistor right there. And so our equivalent 345, or 1 over our equivalent 345 is 1 over R3 plus 1 over R4 plus R5, 1 over the equivalent of R4 and R5, because those two are in parallel, so we've got to add them in parallel. So therefore, 1 over our equivalent of 345 is 1 over 3 plus 1 over 9. So therefore, our equivalent of 345 is 9/4 of an ohm. Go ahead and do that algebra. A pretty straightforward algebra. That should give you 9/4 of an ohm. Okay, so now we know what each of the three resistors in the circuit right here are, and now those three resistors are all in series. So those three resistors are all in series, so they just add, right? 1 ohm for R1, 2 ohms for R2, and 9/4 of an ohm for R3. So the final equivalent circuit looks like this. Not like that, but like this. Our equivalent, we'll just write our equivalent for all of them, and that is equal to 1 ohm plus 2 ohms plus 9/4 of an ohm, which I believe is 5.25 ohms, and yes, I'm not very good at writing the ohm symbol. Horseshoe. So the equivalent resistance of the entire circuit is 5.25 ohms, and therefore the current from the entire circuit, right, delta V equals the total current times the equivalent resistance, if that's for the battery. So therefore the current is 10 volts over 5.25 ohms. Whoops, I said I'm not very good at writing ohms. Therefore the current is 1.9 amps. Done. So there you go. That's just back to the original page with the results in the bottom right-hand corner. Okay, one more example for today. Okay, so here is example number 5. Just thought I'd do one with a bunch of power supplies. Nothing really any different in the way that we deal with this, but I just gave you 3 power supplies, potential differences, 10 volts, 5 volts, 5 volts, 2 resistors. Oops, there were 3 resistors originally. I crossed out resistor number 1, 2 resistors, each of resistance 100 ohms. What is the current through resistor 3? What is the current through resistor 2? They're 2 and 3. I left off one. So how do we address this circuit? Well, it's still just Kirchhoff's rules and Ohm's law, right? It's just loop rule, current junction rule, and Ohm's law. So our 3 rules, just as a reminder, are the sum of the potential differences around a closed loop. There you go. Sum of the potential differences around a closed loop equals 0. Sum of the currents in equals the sum of the currents out of a junction. And the potential difference across any resistor is the current through that resistor times the resistance of that resistor. So those are our 3 things that we use to do circuit analysis. And sometimes doing equivalent circuit stuff helps, but is not necessary part of circuit analysis. So we will apply this, and we can apply this. Let's start by just assuming a direction of current through certain things. Let's go ahead and, well, since V1 is the biggest power supply, then I'm going to assume that current is going in that direction. That means that current is going through R2, going from down to up, going up the page through R2. R3, it's a little harder to say what the direction of the current is through R3. So we're just going to have to guess, and then if we get it wrong, we can go ahead and we'll get a minus sign in the analysis. So there's I2 and there's I3. Those are two different currents. There is actually a third current, which is the current coming around here, right? If we want to write the current everywhere, the current coming around here, I'll just call that, since we already had an I2 and an I3, we'll call that I1. What about the current, let's say, here, right, in the top part? I don't know if you can see that yellow arrow. Red is not good. Let me find, let's use a blue arrow. Okay, what about the current in there? Well, again, because that's continuous with where I1 is, so this is also I1, just making sure we understand this. And what about the current here? Again, that even though there's two power supplies and a resistor, it's all in series, right? The whole thing on the left-hand side through the two power supplies and R2 is in series, so the current here must still be I2. A power supply doesn't change the current, right? So I2 all the way around, I2 all the way around. Okay, just making sure we understand that. Okay, so now we've defined our directions of current so that we can then write down Kirchhoff's laws. First of all, we recognize that we can look at either one of our junctions. Let's just take the junction on top and say that coming into that junction is I2, going out of that junction is I1 plus I3. Okay. And I'll tell you right now that I1 is not relevant really to anything here because I1 is not going through any of the resistors. So that may not be a useful equation. And then we can do Kirchhoff's loop rule, and let's do the right-hand loop and the left-hand loop. We can do we could do the big loop too, but let's just start with the right-hand loop. The right-hand loop being, I'm going to go ahead and highlight it, right? The right-hand loop being this loop here. And so we will go ahead and just start where my blue arrow is, start above the power supply and go in that direction. So as we pass in the correct direction through the power supply, or from minus to plus, we get a delta V3. And then when we go, oh, look, now we're going backwards through the resistor, right? We're going against current I3 through resistor. So that's going to be plus because we're going against the current as we go. I'm sorry, did I say we're going clockwise? I drew the arrow. We're doing the loop rule going clockwise. So we're going, that's what I'm doing. So we're going backwards through the resistor. So that's going to be plus I3 R3 equals 0. And now I want to point out before we go any further that right away tells us what I3 is. We know what the current is through resistor 3. I3 is the potential difference delta V3, which is 5 volts, divided by R3, which is 100 ohms, and I3 is 0.05 amps. Not only is it 0.05 amps, but it's positive, so that means we had guessed the direction of the current correctly. Okay, so now we know what I3 is. We can go ahead and do the loop rule. Let's do the loop rule on the left-hand loop. Where do we want to start? I don't know. Let's just start. Let's start. I'm going to draw an arrow in the upper left-hand corner, and let's go clockwise. Okay, clockwise. So we first go through delta V1. We get plus delta V1. I'm writing this down in the lower right-hand corner. Plus delta V1. And then we go through R3 in the correct direction. So we lose potential when we follow the current, I3R3, which we know I3R3 is 5 volts. We already figured that out in the lines above. And then we go backwards through a power supply. So we subtract it backwards through delta V2. minus delta V2, and then we go in the correct direction through, we follow the current through R2, so we've got I2 R2 equals 0. So again, let me just draw it on the circuit. So on the circuit, I'll just repeat this equation. So we started, and I'm going to make it messy now. So we started here, and we went through the first power supply from minus to plus, so that adds a potential of plus delta V1. We go through R3, and so that along with the current, so we lose potential I3 R3. We go backwards through V2, so we lose potential delta V2 minus delta V2, and then we follow the current through R2, so that we've got minus I2 R2. And then it's the sum of the potentials equals 0. Okay, so some of you probably picked up the error earlier that I made. I made a little mathematical error. Algebra, I know I always say algebra is up to you, right? It's just it's not physics, but shouldn't be making mistakes in algebra, and I made a mistake. And I realized the mistake because the results that I was getting in the end didn't really make a whole lot of sense. I was doing some stuff in my head ahead of time. The error that I made is I've just gone back to the circuit, taken away a lot of the scribblings. In the lower right-hand corner, I still have my equations, the junction rule, the loop rule, and then the result from the loop rule. The result from the loop rule is that I didn't do the algebra right, and I3 is negative. I3 is negative 0.05 amps, and I said explicitly it was positive, and some of you must have been saying, what? There's something that he's seeing that I'm not seeing. And so the current I3 is in the wrong direction, so the current I3 goes upwards. So the current I3 is in the upwards direction. Doesn't change any of the rest of the analysis, everything else stays the same. So now we're just going to solve the third equation to find I2. So I3 is 0.05 amps going from bottom to top, right? So the answer to part A is I3 equals 0.05 amps going upwards through resistor R3. I'm just going to draw that arrow. And then part B, we're still going to solve the next equation, which is delta V1 minus I3 R3. But I3, remember, is negative, the way we wrote down these equations. Careful. Here, let me write this down first. Okay, so I just copied that equation there. But this equation was written with I3 going down. We found that I3 was negative, so we either have to change the sign in front there or just keep track of the fact that I3 is negative. When we wrote the answer to part A here, we said, oh, I3 is negative, so the absolute value is 0.05 amps. It's going upwards. Okay, so in B, we get delta V1, which is 10 volts, minus negative 0.05 amps times 100 ohms, minus 5 volts, minus I2 R2 was 5 volts, equals 0. Gosh darn it, sorry, I wrote that down wrong. I'm writing down this equation. Sorry, I'm writing down this equation at the bottom here. And I wrote minus 5 volts instead of minus I2 R2. Minus I2 R2, which is 100 ohms, equals 0. And so now we got to solve for I2. So therefore, I2 is equal to 0.1 amps. That's what we get. I2 is 0.1 amps. And so now we're done. That's part B. Part A, 0.05 amps. Part B, 0.1 amps. And then the direction, in both cases, the current is going through the resistor in the upwards direction. Current is not a vector, but it does have a direction. I know, it doesn't make a whole lot of sense. We haven't really talked about that. But it's not a vector in the sense that we say that current goes... the current density is a vector, remember, when we talked about current density. So current is really a component of that current density. So current has a direction associated with it due to the fact that it's a component, but we don't treat it like something that's a vector. But we can definitely talk about the direction of the current as being through resistor, to left, to the right, up, down, etc. Just make sure now this makes sense. To me, what didn't make sense is when I calculated it using the wrong sign, the directions didn't make sense. But now we can see that the currents make sense in terms of what they're doing with the power supplies, right? That I1 goes in that direction, I2 goes in that direction, I2 goes backwards to this power supply because it's in series with a bigger power supply, so it goes backwards to that power supply. It's in series with delta V1, which is pushing in the other direction. And then I3 actually comes out, and I3 and I2 add to be I1. So I1 must be 0.15 amps. I never asked what I1 was. I said we don't care what I1 is, but it's 0.15 amps. Okay, and since I'm always terrible at jokes, let me try one more from Siri. Hey Siri, tell me a joke.
A telescope just turned up in our lost and found box. We don't know who it belongs to, but we're looking into it.
Haha, Siri's better at jokes than me, and that was a physics joke too. Okay, see y'all later.